सबसे पहले मैं थोड़ी सी बात आप लोगों से करूंगा असाइनमेंट्स के बारे में, और बात जो है वो ये कि it has been discovered that many of you have been cheating in assignments. Cheating in the sense that you have been copying from someone else's solutions. Obviously, there is a way to stop it. There can be, for example, punishments. There can be penalties. And I think there will be some penalties. But instead of relying on penalties exclusively, I would like to actually try to understand why is it important that you do not copy assignments from others. I would like you to understand this. When something is explained to you in the classroom, it is sort of one aspect of the whole phenomenon that is explained in a most general form. And the rest of the work is left to you in the form of doing problems. In most cases, problems are given at the end of the chapter, and chapter problems usually are meant for you to practice your understanding, check your understanding of the subject. And if you are not able to solve any of those problems, then you need to actually go through the chapters again, try to understand a little more, and then attempt the problems again, and so on. It is an iterative process through which you get to not only have a better understanding of the subject, but also get to apply the knowledge that is conveyed to you in some of the basic principles into actual concrete problems. Now, what happens if you do not solve those problems yourself? You will simply fail to acquire that capability. The capability that is always there for you to acquire. Why should you not acquire that capability? It is there for you to acquire. You can just put in a little bit of effort and acquire that capability. Why should you refuse to acquire that capability? And if you find an easy way out by copying somebody else's solutions, of course you will never put an effort to solve those problems. You will never put an effort to actually try and understand and then get to completely, understand the problem, understand the subject. This is your loss. As simple as that. Nobody else's loss. Your loss, completely. So, instead of relying on penalties, I would urge you to understand this point. I would urge you to see that there is a chance for you to understand the subject in its full scope, and that by not doing it, you are hurting yourself. Okay? That was the first part. I hope you understand this point. The second point, still there will be penalties for those who copy from others. I think number 2 point should be not just penalties, but other than that, there should be an honor system. Not to try and do any cheating at all, anywhere. Be it cheating traffic light or cheating a shopkeeper or cheating somewhere else. It should become a part of our life. We should simply not cheat anywhere. And if we cheat at one point, then perhaps cheating at other points becomes easier and simpler for us. We, just that barrier to cheating and dishonesty goes away. What happens? We lose our honor. We lose self-esteem, I hope. And that, I think, is a very bad thing. So, maybe it makes life easier, but it makes life less meaningful. I hope you understand this point. The third point is that there will be penalties. And the penalties will be both for those who copy and for those who let their assignments be copied. For both of them. Their assignments will be cancelled. They will get 0 marks for them. Your copying has been noted in the first 2 assignments, and they have taken note of who copied where, and since I had not yet warned you, therefore penalties will be deferred in those cases. If no further copying incidences for the same people are found in future, they will not be penalized. But if in future the same people are found to be repeatedly, and even after what we said today, are found copying, they will be penalized not only for those coming in future, but also for the past ones also. Okay? This is a decision to which we all came when we had a meeting among teaching assistants and all of us. We said that this is what we will. Also, I hope when there is a benefit of collective study, combined study. You sit down together, 4 or 5 of you, and study together. You come to understand things faster, help each other, go through the process of thinking, which is all very good. I am not discouraging that. But it should not lead to completely identical answers as well as procedures as well as explanations. That is not expected of such combined study. You study, you understand, then you go back to your corner and do it yourself. And then not give it to anybody else, because that other person may copy it and land you in difficulty. Okay? So what I have told you is no big deal. It's all very common, and you are all grown-up people. You all understand this very well. So I hope first 2 points that I raised would make an impact on you. The last point may or may not be very important for you. Okay, I received through the your teaching assistants of the course. I received 2 questions that arose in your recitations. One was about change. These are both about entropy, and the question is the change in entropy in an adiabatic process always 0? Is the change in entropy in an adiabatic process always 0? Hafsa, this was the question? Yeah. My answer to this question is that depends upon which contributions of the dynamics of the body you are taking into account. If the process is only exchange of heat, then certainly in a adiabatic process there is no heat exchange taking place, and therefore the change in entropy would be 0. But there can be other things also. And I think one of the examples we had taken in the last lecture, or maybe before that, where we had this free expansion of a gas. In the free expansion of a gas, in a completely insulated environment, no exchange of heat, dq is equal to 0, but because a larger volume was being made available to particles, therefore entropy increased, and we calculated that entropy. Okay? So entropy can change, should change on account of various things. One of them is the exchange of heat, but there can be other things also. And that will take us to actually the most fundamental properties, the origin of entropy. Entropy is a macroscopic parameter. As I said, thermodynamics is all about macroscopic parameters, the parameters that you can directly measure and fix in laboratories. But the origin of entropy is not macroscopic. Origin of entropy is microscopic. It comes from microscopic considerations of particles. And therefore, we will need to understand the macroscopic origin of the concept of entropy to understand when will entropy be 0, when will it be positive, and what happens when it is negative. Okay? We will need to understand that. And the second point that was raised was, I hope this answers the questions. Hafsa, would it? Ask the class. Okay. I don't know who asked this question, but does it answer the question? All right? No nods except for one. So only one person understood this point. Okay. The other question was, can a reversible process have a non-zero entropy change? I had written over here that entropy change for a reversible process is 0. Okay? And I had said that ds, delta S is 0 for reversible, it is greater than 0 for irreversible processes. Now when you say non-zero entropy change, now that change needs to be qualified, because the law is entropy always increases. But we also saw in all the detailed calculations that we carried out in the last lecture, bits and pieces of entropy in going from this temperature to this temperature, then melting, and this temperature to this temperature, and so on and so forth, that there are situations where entropy can be negative in a particular process. Not overall, but a particular process. And therefore, entropy change would be negative. And in those cases, the law that in reversible processes entropy change should always be increasing would amount to saying that entropy change of the system plus the surroundings, what is usually called quote-unquote universe, entropy of the universe would always be increasing in irreversible processes. Okay? In reversible processes, entropy of the universe as a whole will be equal to 0. So this entropy may decrease, but then the entropy of the environment may increase, may compensate for this decrease at some particular point. So decrease and increase go together, and when you make the statement ds is greater than or equal to 0, delta S, oops, the chalks happen to be the same chalks, eh? मैं आज इनको देख के खुश हुआ था कि ये तो अच्छे चौक लग रहे हैं. Delta S, no, greater than or equal to 0 is for system plus surroundings. As a law. Okay? I hope that also answers the question. Any other question about this? It is good that you asked some question. It was good. I needed to be clear in my lecture the last time. Yeah.
So in the first question, so it means that for the adiabatic process, the change in entropy is not zero.
No. Our question is, in my first answer, the first question that I said, is the change in entropy in a adiabatic process always zero? So her question was, does it mean that in change in entropy in an adiabatic process is not zero? It doesn't follow. No. As I said, not always zero. Not always zero. There can be situations which can be adiabatic, yet entropy is change is not zero. Okay? And I gave you the example of this expanding gas. All right. Any other question? Areva, thank you very much. Any other question? Okay. So let me recapitulate a few things about entropy. Yeah.
I have a question regarding one thing. So we mentioned a couple of times that by making a process slow, we make it quasi-static, and that would finally translate to saying that
it's reversible.
It's a reversible process. So can you explain a bit how would making a process slow make it reversible?
Okay. The question is, I had said that a process can be made reversible if it is run quasi-statically. So how can a quasi-static process become a reversible process? The point is that a quasi-static process is the one in which the change is very small and the system is also allowed to come to equilibrium immediately after the change. So it essentially goes from one equilibrium state to another equilibrium state, which is only very slightly different from the previous one. And therefore the changes that have taken place inside the system would not be drastically different. And therefore if you try to retrace the path, you will get back to the same system, same situation. And in that sense it is reversible. Okay? Okay. So remember about entropy. Number one, rules for increase of entropy apply to entropy of system plus surroundings, as I said. And at the local level, entropy may increase or decrease. And spontaneous processes are always irreversible processes. The processes that take place spontaneously without any work being put into them are always irreversible processes, and therefore in spontaneous processes entropy will always increase. All right. Entropy change of the universe during a reversible process is zero. Of the universe, of the system plus surroundings in a reversible process is always zero, although entropies of parts of the system may change. Okay, all of this has been sort of reiterated for you to make sure that this is something which leaves no confusion around. Okay, I will come to the microscopic description of entropy in a minute, but before I go to microscopic description, let me show over here why we say that delta S is greater than d q irreversible by t. I have put a subscript irreversible to show that this change in exchange of heat is taking place in an irreversible process. And this can be seen if we imagine that there is the two states here, 1 and 2, and we take the system from state 1 to state 2 in an irreversible way, and then from this to this in a reversible way. So we actually perform this kind of experiment in which you have two states. Maybe this is a PV diagram. Is it too small for the people at the back side? Okay. So this now is a grossly exaggerated picture. Okay. This is like an isotherm or some reversible process, and perhaps this is an irreversible. This is schematically reversible and irreversible processes through which you could take the system from point 1 to point 2 and then point 2 to point 1.
सर अगर आप स्टेट 1 से स्टेट 2 में जाते हैं irreversible process के थ्रू, तो आप स्टेट 2 से स्टेट 1 reversible process में कैसे लेके जा सकते हैं?
क्यों?
सर क्योंकि वो तो हम ट्रेस बैक नहीं कर पा रहे ना पाथ.
No. We take the system in this way and come back the system this way.
Slowly and progressively.
Well, whatever is a reversible way. Okay? We are going in such a manner. If this path is reversible from here to here, it doesn't mean that it has to follow this path. It can go very quasi-statically on this path so that it is a reversible path. Yes?
Sir, the change in entropy that we're measuring, is it the change in the universe or the system?
We will take this to be the change in entropy of the system. Okay? I'm trying to show this to be basically the statement is that delta S is greater than or equal to change in exchange of heat, change in heat, or the amount of heat exchanged divided by temperature. Okay? And I'm trying to show the first part in this manner, and I'm taking this to show that this will go this way. So, you see, we have already seen in the case of from the example of the Carnot cycle that for a reversible process, delta S is equal to dq by t. We have already seen this. All right? To be able to see this relationship, we need to show this. And this is what I'm trying to do. I'm trying to show this particular relationship. And for a reversible process, for the reversible process, you will have S2 minus S1 equal to integral 1 to 2 dq reversible by t. And since this is a cyclic process, so Clausius' theorem says that this by t over a closed path is always less than 0. This is Clausius' theorem. And therefore, what we are saying is that integral from 1 to 2, I hope now dq irreversible by t plus integral 2 to 1 dq reversible by t is less than 0 according to the Clausius theorem. Okay?
So dq over t shows state function, right? So isn't it true for all state functions that in a closed path the change is 0?
Yeah, but we are at the moment, for a closed path, dq by t would describe certain path, okay? We will eventually take dq by t to be the state variable entropy. We will eventually take that to be re-entropy. And what we have done is we have said that for a state variable over a closed path, this is equal. All right. What you're saying is that for a closed path, a quantity like this should have been equal to 0 because this is a state variable. But what we would actually, the thing that you saw in the case of Carnot cycle was for the reversible process. Was only for the reversible process. And if for a very general process, the Clausius theorem is this.
It means that entropy is a state variable only for reversible.
No, then we will come to a conclusion that entropy is defined for both reversible and irreversible, and therefore the final formula of entropy would be something like this or something like this. Okay? So what we are saying over here is that this quantity from here, I can immediately see that integral 1 to 2 dq irreversible by t is less than S2 minus S1. And therefore, I am writing over here the conclusion that delta S, which I write as S2 minus S1, has two values. One, it is integral 1 to 2 dq reversible by t, and it is greater than, or this is equal to this, it is greater than integral 1 to 2 dq irreversible by t. And that is what I wrote in general case over here, where the equality holds for a reversible process and inequality holds for irreversible process. And when for isolated systems, which means systems plus surrounding, since then heat dq is equal to 0, therefore delta S is greater than or equal to 0 is the statement. This was one point that I needed to explain, and I'm coming to now the microscopic origin of the state of the notion of entropy. Okay? Macro systems, thermodynamic systems, have states that can be described as macro states, macroscopic states, and microscopic states. Macroscopic states we know. These are the things, these are the states which are described by large scale parameters like the volume, like energy, like temperature, like pressure, things of this kind. These are macroscopic parameters. So macro parameters are energy, pressure, temperature, and number, and volume, etc. These are large scale parameters, and they describe the way you look at systems in your laboratory. Microscopic states of the systems are states of particles, or states in terms of the particle in terms of constituent particles. So there would be the kinetic energy of individual particles, and there will be potential energy among particles, there will be masses of particles, and there will be angular momentum of particles, and so on and so forth. So these will be the atomistic, molecular properties of the constituent particles, and those would be the microscopic properties. And then if you define states in terms of those details, those will be the microscopic states of the system. So for example, I'll give you a very crude example of a very simplified nature. Suppose you have a box in which you have only, 4 positions and 4 particles. So if you have these 4 positions given by 4 boxes, and you have 4 particles to be accommodated in them, then you have this state replicated in several different ways, in which it would be one in which there is all the 4 particles are here, another one in which all the 4 particles are distributed in this manner, another one in which there are 2 here and 2 here, another one in which there are 2 here and 2, and so on. I could make a large number of such systems. So it is the same system of 4 particles, but this system of 4 particles has very different microscopic configurations and a large number of microscopic configurations, a very large number of them. And when you say the macroscopic states of the system, I mean these states, which differ with respect with each other in terms of microscopic details of how many particles are occupying which box, kind of a state. So this will be different from this, and then these are all different microscopic states of the system. And what you do is that you actually then calculate probabilities of the system being in any one of these states. Any one of these states. Okay? So this is the job that requires statistical calculation, and therefore the discipline is called statistical mechanics. And it is statistical mechanics that you will learn after maybe not the next semester, but the semester after that. You will learn, or maybe the next semester, you will learn statistical mechanics. So where you will learn thermodynamics, all thermodynamics that we learned here, or you will derive this thermodynamics from statistical methods, from microscopic considerations, looking at the states of the system in macroscopic detail. Okay. Now when you do this, then you think of the collection of such microscopic states. microscopic states. And then you will conclude that, look, the probability of finding, now this P stands for probability, okay, not for pressure. So I will also put an index to it. Probability of finding the system in state R would simply be, by the laws of probability that you have learned so much, will be equal to number of states of the kind R that you are looking for, number of times the state R occurs, divided by the total number of possible states. Okay, this is the usual way of calculating probability. So this will be number of times the state R occurs divided by total number of possible states the system can be found in. So if you were over here, we would go on doing this exercise and calculate the total number of possible states, and then we say, what is the probability of finding all the 4 particles in one box? And we will be able to quickly tell that there would be 4 of these out of all of these, and we would be able to tell what that probability is. Okay? And another quick example that I have before me, and I want to take up this quick example for you to understand what I'm trying to tell over here is the example of which is what everybody says in the case of probability, 2 dice. You have these squares with numbers on them, on their faces, and you want to calculate the possible number of states, and perhaps you will have these numbers on their faces, and you want to know probability of finding a certain number on top. And I'm taking the example of 2 dice because the collection of microstates, I will call the collection of microstates as the usual name that is given to it in statistical mechanics as ensemble. Ensemble, French name word for assembly. So a collection of states. Okay? And I will write down over here the ensemble for it. And the ensemble will consist of the situation of the possible states. The die 1 has a 1 on top, the die 2 has a 1 on top, the die 1 has a 1 on top, the die 2 has a 2 on top, 1 on 3, and 1 on 4, and so on. And then the die 2 has a 1 on top, and die 2 has a 2 on top, and a die 2 has a 3 on top, and a die, and so on. And then etc., etc. All of this. Okay? If you look at this, has 5 on top, or die, this has a 5 on top, and then 2 has a 4 on top, and 2 has a 5 on top, and 2 has a 6 on top. Total number of possible events when you throw 2 dice together is 36. For each one of these, there are 6 of these possible. These 2 dice are completely independent of each other. Okay? And therefore, for each of these, there are 6 of other possibilities, and each of these, there are 6 of these possibilities, and therefore, total 36 number of possibilities. Of these, so the ensemble consists of 36 possible states. Of this, you will, if you want to check the event that you want, the probability of which you want to calculate, if you take the event as the sum of numbers on top, then the sum number can be 2 and 3 and 4 and 5 and 6, 12. That is it. There can't be anything less than 2, there can't be anything more than 12. And if you look at the number of times each one of them occurs, then this occurs only once, this occurs only once, this occurs twice, and this occurs thrice, and so on. And 11 occurs twice, and 10 occurs thrice, and 9 occurs 4 times, and 8 occurs 5 times, and 7 occurs 6 times. Okay? So here one can make very quick statements about the probability of a particular event. Using this, you say, what is the probability of having a total of 5 on top? And that is equal to 4 over 36. 4 times the total comes to be 5, and the total number of events is 36. So this is a very, very simple a review of the basic probability that you already have learned. We now go to talking of entropy defined in statistical ways. Entropy is defined as sum over all microscopic states, sum over all, this I describes microscopic states, and there's a minus sign here. I should make it clearer. Minus k times summation over I, pi log pi, where pi are probabilities of event I. And this is how entropy is defined. Each of these probabilities, like any probability function given in that definition, goes from 0 to 1 in value. Probability has value from 0 to 1, and because this function log of a quantity that goes from has in the argument of which is between 0 and 1 has a negative value, and therefore you have a minus sign outside. Okay, to make entropy a positive quantity. And if you were to use the basic what should I say, the assumption of what is called equal a priori probability equal, this is an assumption which says that if you are given a system which is like a thermodynamic system, it exists in a large number of states, then the starting assumption is that all these states occur with equal probability in a system which is completely closed system. Equal a priori probability means that all the probabilities to start with, when you start the thing, then you say at that point, at the start, you say all the probabilities are equal, which means that probability pi is equal to 1 of, I'm going to use this number omega to show total number of possible states in the total number of states in the ensemble. Total number of states that you can make of such a system. Total number of ways in which you can describe the system, microscopically describe the system. That is the total number of states in the ensemble. Because you say that all of them have equal probability, therefore the probability will be equal to 1 over the total number of possible states.
So what is ensemble?
I just wrote over here. No, I just wrote over here. Collection of all microscopic states should be called in English assembly of systems, but physicists often take terminology from other languages also. So they took it from those people who were describing this thing. They were French, say they used ensemble. And every physicist everywhere in the world, even in Russia and China, says ensemble. So we better also say ensemble, okay? And not feel very strange about it, okay? So this is total number of possible states, microscopic states that can be built for a system. Total number of macroscopic states that can be built for the system. And since all the probabilities are equal, therefore the probability of each one of them is simply 1 over omega. And if I substitute this in this expression, I will get minus k and then sum over I and then 1 over omega and then log of 1 over omega. And log of 1 over and sum over, now there is nothing being summed over I, so I can perform this summation. This summation is total number of macroscopic states, which is equal to omega. So this is equal to minus k omega times 1 over omega times log of 1 over omega. All right?
What is k?
We will come to that in a minute.
So how do you put omega there? Should it not be I times that thing?
No, I is the sum over all possible states. And we said sum over all possible states is equal to omega. Okay? And we said that this is 1 over omega as it is. Log of 1 over omega I kept as it is. And sum over omega I replaced because there is nothing being summed over now. So sum over I is equal to simply omega, number of possible states. And that is equal to omega. And therefore, this says that S is equal to, now this is 1 over omega. So I can further change it to minus k omega. Okay, omega and omega cancel out. We know that. And minus k log of 1 over omega. And therefore, S is equal to k log omega. This is a very fundamental relationship in physics. Boltzmann derived it. And this was considered such an important development that Boltzmann tombstone has this formula written on it. So, in the city of Vienna, you find Boltzmann's tomb, and their tombstone says S equal to k log omega. And that has become the identity of the person also. This relationship, I showed the equivalence between that relationship and this relationship for a particular reason. The reason being that actually there is something else also which has this shape, and this was shown by somebody called Shannon in about 1940 or 1945 or so, when he said that in the information theory, loss of information is equal to minus sum over I pi log pi. Okay? He was talking of loss of information, which is also, he called actually uncertainty. उसका K नहीं है. यहाँ पे K इस वजह से है कि ये किसी ने सवाल पूछा भी था कि K क्या है. K is Boltzmann constant. और आपको इस वजह से ये मालूम होगा कि चूंकि ये नंबर है, लॉग नंबर है, तो एंट्रोपी की डायमेंशन सारी की सारी K के अंदर होनी चाहिए ना. और अभी हम बात कर रहे थे कि एंट्रोपी की डायमेंशन वही है जो हीट कैपेसिटी की है, तो हमें ये भी ध्यान में रखना चाहिए कि एंट्रोपी की डायमेंशन जो है वो बोल्ट्जमैन कांस्टेंट के अंदर भी है. वही जूल पर केल्विन जो डायमेंशन है एंट्रोपी की, वो हीट कैपेसिटी की भी है और बोल्ट्जमैन कांस्टेंट की भी है. ओके, यहाँ पे ये ज़रूरी नहीं है किसी कांस्टेंट की. कोई कांस्टेंट आपके पास अगर हो तो वो अलग बात है, डायमेंशन की ज़रूरत नहीं है. दिस इज अनसर्टेनिटी, व्हाट यू कॉल अनसर्टेनिटी. इफ यू हैव सम इंफॉर्मेशन दैट यू रिसीव and out of that information you have some information missing, then that missing information is in the theory of in information theory you find it from a relationship like that. And जब आप इसको डिटेल में पढ़ेंगे तो आपको मालूम होगा कि इस फंक्शन को में एक्चुअली विद द प्रोबेबिलिटीज you can actually, this particular relationship you can, मैं यहाँ पे ज़्यादा करीब आ नहीं सकता, एकदम गूंज पैदा हो जाती है. If you have uncertainties in the events, in some events, and you can think of some experiments where you can create uncertainties, then you can actually show that this function would describe those uncertainties. Okay? So, but that actually allows us to relate entropy with this particular information, uncertainty. It tells us that entropy S is loss of information. Increase in uncertainty about the system. And if you want to be convinced, I can actually take you to that simple example that I gave the other day, when I said we have a box and we have a partition and gas is all over here. And then I take out the partition and allow the gas to expand everywhere. Then actually over here I am a little certain, if I am asked where the particle is, I can say with certainty before opening the partition. I can say with certainty that the particle is on this left-hand half of this box. But when I remove it, the particles have all now gone on this side and that side, and that has increased the uncertainty of finding the particle.
But there is every time a certainty that it will be in the box.
There is an uncertainty.
वो तो certainty हमेशा रहेगी ना कि वो box में तो है.
In the total box, yes, yes. So in the total box, there will be, it will be certain that the particle is in this entire enclosure. But then the uncertainty is that earlier the particle was confined to this, now it is everywhere, and we actually calculated entropy for this. We did, and we found that that was proportional to log 2 because the box was, sorry?
System define करते हैं कि इसके लिए uncertainty दें.
Say that again. If we define system to
आप एक frame define करते हैं ना कि हम इस जगह के लिए uncertainty दें.
uncertainty in the, okay, when I said uncertainty, I mean over here I'm talking of entropy. Uncertainty in the sense that the particle was initially certain to be found over here. Now it is not certain that the particle will be found over here. Okay? So the uncertainty has increased. Okay. I can take another example. If we have some, for example, we talked of that also, a glass of water, and if you drop in a bit of ink into it, drop of ink into it, then it will go and mix. That particular process, we said again, was a irreversible process. It was also a process in which the ink particles were dissolving and getting into mixing up with water everywhere, and after a while they will mix nearly everywhere uniformly, and it will be the location of ink particles will be difficult to say unless you say it is anywhere within this jar. Initially it was only in this small drop that was being dropped into this. Okay? Now it is nearly everywhere. So the point is that there is this loss of information that is contained in inherently there in irreversible processes, and that loss of information is captured by the thermodynamic parameter entropy.
So you said that delta x for the universe should be greater than or equal to 0. So that means that for the universe there is a net loss of information. But don't physicists tend to disagree on that?
No.
They say that information cannot be lost from the universe. As the information paradox well.
No. Entropy of the universe in the sense of system plus surroundings is increasing, and therefore there is a loss of information. The entropy would remain constant only in the case of reversible processes, and entropy of the of some systems can actually become less, can reduce, but only locally, but at the cost of an increase of entropy outside, so that when you sum them up, there will be an increase, overall increase. So the entropy of system plus surroundings, the entropy of the universe increases. Okay? So there was a time, and in fact even now, people say that if the entropy of the universe is increasing all the time, therefore there will be an entropy death of the university, because entropy will continuously increase and increase to a level where then it will become very difficult, because entropy is related to temperature in some manner, and we will see in what manner, and that would amount to heating up of the universe, and therefore there will be death of the universe. But that is something which is only sort of concluded from this statement. There is a third point that I wanted to bring in here, and the third point was about this is again in the realm of microscopic study of systems, in the realm of macroscopic origin of the function entropy. And this is to do with what is called Boltzmann H theorem. And since we have already now seen how microscopic states can be defined, it will not be difficult to understand Boltzmann-H theorem. Boltzmann-H theorem says that there is a quantity that Boltzmann defined as H, which was summation over I, Pi, log Pi, again P being probability, Pi being probability of the ith state of the system. And Boltzmann-H theorem says dH by dt is always less than or equal to 0. dH by dt decreases in nature. And I will take some time to prove this also, because I think we have the means to
What is H?
is Boltzmann's function H. Okay? Boltzmann just took out of his hat a function called H, and he said, look, this is this function, and this function is going to decrease with time.
So we defined entropy here by saying that it is equal to minus k summation
Right.
just a log of phi. So what is the justification behind this? How is this actually derived?
Okay, so the justification for deriving this expression has been Boltzmann's H. When Boltzmann's H was the theorem, H theorem was shown, proved in some manner, and a relationship was seen that if such a thing could decrease in time, and we see entropy increasing in time, if suppose there was a time evolution of things, then there was a direct relationship between that and entropy, and this is how it was shown. In fact, the first thing entropy was shown was in this particular form by Boltzmann, by saying that if you have a large number of possible microstates of the system, so actually the information problem is here too. If you focus on this, the problem of loss of information is here too. The larger the number of possible microstates of the system, the larger the entropy would be. Okay? Because this only calculates the number of microscopic states of the system. So if the system can be found in a large number of microscopic states, then there is a larger uncertainty in defining microscopic states of the system, and larger the value of entropy. All right? Because there is a large number of microscopic states of the system, so to say that the system is any one of them would become the probability of that will become smaller and smaller, and hence there will be a larger uncertainty about things, and entropy is directly related to that. Okay, in this particular lecture, I'm trying to squeeze in various different explanations for the function entropy. I will leave out to you to go through a number of texts to convince yourself, of course through exercises also, to convince yourself that this is how different phases of entropy are to be seen, but then also try and put them together here too. So what I intended to do was to actually show a thing like this. Boltzmann's H theorem. And this theorem comes in the following form. If I were to take if we take H equal to summation over I, Pi log Pi, and if I want to take dH by dt, I will have it as summation over I dpi by dt, then log pi, plus I will have pi times 1 over pi log dpi by dt. Is that very clear to everybody, or shall I explain this also? Yeah? Okay. No big deal. I only differentiated this part. This is differentiating this part and leaving it as it is, and then leaving it as it is and differentiating this exponent. This thing, differential over log p is 1 over p, and then dp by dt. So this is actually summation over I log pi plus 1 multiplied by dpi by dt. Okay? Now, let us look at dpi by dt. This seems to be an important thing. How would the probabilities change? Pi is the probability of finding the system in the ith state. Okay? And how would that change in time? That would change in time by noting that there is this ith state and there is this jth state. Some particle would make a transition from I state to jth state, and at another time it will make a transition from jth state to ith state. It will sort of, there will be a transition probability, and I'll call it pi, and I will have to give it some indices also. So this will be pi ij going from I to j, and this will be pi ji going from j to I. These will be transition probabilities. And in equilibrium, there will be as many transitions from I to j as transitions from j to I. In equilibrium, if the system has reached a particular state of equilibrium, there will be as many transitions from taking you from state I to state j as from j to I. So you say that, look, dpi by dt will be equal to I left out that page. Okay. Will be equal to summation over all other states. There will be a transition from state I to state j to any of these states j, and that will be when particle exists in state I, pi, particle has to exist in state I, and then probability, and then the probability in going from j to I to j, this will give you system going from state I to all the other possible states, can go to any of these states. That is given by this expression.
So summation j
because it can go to any of these states. So it is essentially, there will be a probability of there will be particle going from state I to state I plus 1, to state K, to state S, to state T, and so on and so forth. And you have to have a sum over all the states. And then there will be the other situation where you have particles coming in from state J to state I. Okay? Sorry? नहीं, अभी तो मैं इसके दरमियान साइन लगाने वाला हूँ मैं. Okay? We are looking at change in the probability of the ith state, and that will be all the particles coming in from outside, and this is all the ith particles going to other possible states. So I put a minus sign in the sense that this is, ये बहुत डिस्टर्बेंस है आवाज़ की, हैं? क्या करते हैं? बहुत ज़्यादा ऊंचा हुआ है क्या ये? So this term is transition of particles from all other states to the ith state. So they have to first of all exist in all the other states, and then they have to make a transition from that state to the ith state, pi ji. Okay. If you are looking at the change in the probability of the ith state, then you will say there is a term which will increase. Thank you very much. There is a term, अभी भी हो रहा है कुछ, अभी भी इसमें गूंज है, थोड़ी सी कम करें आवाज. Thank you. अरे भाई, मैं बहुत करीब हो गया ना, इसकी वजह से हो रहा होगा ये, है ना? चलें, in the last minute or so. ये जो है मैं इसको एक्सप्लेन कर दूं, उसके बाद फिर मैं ख्याल है परसों के लेक्चर में आई विल कंटिन्यू विद दिस. ओके, ये बता रहा है रेट ऑफ चेंज ऑफ द प्रोबेबिलिटी ऑफ फाइंडिंग द सिस्टम इन द ith स्टेट. So there is this ith state in which system can be found and has a probability, and that probability can change with time. How will it change in time? When particle goes out of the ith state and other particles can come into the ith state. Okay? So there will be this process which will increase the population of the ith state. Oh, this is going from out. Okay. So I have to actually then do the other way around. Okay? You are right. So J, Ji, and I and Ij. Okay, this will describe population of the ith system increasing, and that has to be positive. This will describe the population of the ith system decreasing, and that is why there is negative sign over here. Now, the rest was to be only 3 or 4 more steps to show the conclusion that I wrote over there, Boltzmann's conclusion. अब आपको यहाँ पे जो असल चीज़ बताने की है वो ये है कि this is just another angle. एक information theory वाला angle है, loss of information, uncertainty function has the same form, Boltzmann's H has the same form, and it shows a basic law which shows that this H quantity decreases in time, and that all of these things are to be combined with our own concept of entropy.